Log on, tune in, find out. Another good idea from Cambridge.
Well, I'm glad everybody's back. So we have three speakers for this session. The first speaker is going to be Bill Notz from Ohio State University. He's going to speak on sequential experimental designs for computer experiments. Bill.
All right. I'm not going to answer any of the questions that were raised in the last session, and about all I can say is something from The Wizard of Oz, is that we're just back in Kansas. So this is joint work with a student, Aaron Kwan, and it's really motivated by a paper by Moore, Lewepke, and Williams, and some discussions I had with Brian when I first heard him speak about this. So let me give you some background. So again, the context is computer experiments, and I'm going to consider a deterministic computer experiment with a slow computer code. It produces a deterministic output at input x, and for the most part, I'm assuming x is just the unit square for the purposes of this design talk. I'm assuming there's a well-defined goal that you're running the computer experiment for some purpose. Possibilities are to determine the input that yields the optimum output. That was the focus of a lot of work of Will Welch's students, and one of the important papers was this paper by Jones et al. In 1998. Another possibility is to determine the inputs that produce a given value of the output. There's a paper by Ranjan and Derek and a bunch of people in 2008. There's some work by Tom Santner and some of his students that have to do with determining Pareto fronts. Or maybe you want to find a fast emulator that is a good global approximation to the simulator, and there have been some papers about that. This Ruiken paper in 2003 surveys a lot of different approaches to that problem. So to accomplish this goal, we observe the simulator at endpoints. I'll call that the experimental design. And we're going to fit a gas model. This isn't absolutely essential, but just to keep things simple, let's assume we're fitting a gas model to the output. And we use this fitted model to help us accomplish our goal. And I'm just going to assume you're all familiar with gas models and EBLUPs and so on. At this point, if you haven't figured it out, you're probably completely lost, and my talk is not going to save you. So design involves the selection of the inputs at which to observe the simulator, and I'm going to assume the following, that we're going to use a sequential design. And by this I mean a few inputs are selected, the simulator is run at these inputs, and based on what we observe, we decide where next to observe the simulator. So we try to learn something from previous observations to guide us in choice of design. And throughout this talk, there's a clear optimal design flavor. And since I was trained in optimal design, it's hard for me to completely forget my background. I'm assuming we have m greater than 1 computers available to run the simulation, so we can observe m inputs simultaneously. So it doesn't have to be one at a time sequential, it can be m at a time sequential designs. And I'm assuming the number of observations we're going to take is an integer multiple of m, so what we do is we run the experiment in b batches of m inputs. And observations from the previous batches are used to determine the inputs for the next batch, and I'll call that batch sequential designs. That's really not my term, but that's what we'll refer to it here. And we have some criterion for selecting inputs so as to facilitate the goals of the experiment. And in the example I'm going to go through, I'm going to assume we're looking for an optimum because it's an example that some of you are familiar with. And the criterion that I'm going to focus on are things like improvement criteria. In fact, that's exactly what I'm going to focus on. But others are things like mean square error that you could use, entropy. Those are some possible criteria you could use to select inputs. Improvement criteria lend themselves to one at a time sequential design, so that the next point is the point that maximizes some function of the data observed so far. And Alex sort of talked about that in his talk. So we saw an example of that where he had one at a time sequential using an improvement criteria. And the example he talked about and that I will refer to is the one in Jones. If you haven't seen it, this is the criterion here. His improvement is F min is the smallest observation you've observed from the simulator so far. Y of x is sort of your model at x. And the amount of improvement you get improvement if at x, y is smaller than anything you've observed so far. Otherwise, there's zero improvement. And that's a random variable. So what Jones, et cetera, do is they calculate the expected value, and this is the expected value. So the expected improvement is the x that minimizes this expression, where this is the BLUP, this is an estimate, drop the x off here, this is an estimate of the standard error, this is the normal density function, this is the CDF for the normal distribution, and so on. So this is what you get when you calculate the expected value. And that's the function that tells you the improvement. And so you take your x you take your next observation where this function is maximized. Now, what Loepke, Moore, and Williams discuss is this idea of batch sequential design. And there's a couple of things that come out of this paper that seem counterintuitive to me. And maybe it's just me, but I'll tell them to you anyways. It turns out it's not always obvious how to implement some improvement criteria which work well one at a time, work well in a one-at-a-time sequential manner in batches. So in particular, they make the following statement, that methods relying on the data, that parentheses shouldn't be there, Y are not readily extendable to a batch sequential strategy. This includes strategies based on improvement criteria. So they didn't know how to do this. And so in their paper, they just, when they look at some criteria, they do it one at a time rather than in batch mode. What they wanted to do was say, I want to select a set of m points, and I want a criteria that's a function of a set of m points. And it wasn't clear how to do that with improvement criteria. But they were able to do that with other criteria like mean squared error. And it turns out that in their study, the methods that performed best were either an entropy-based approach or some distance-based space-filling approaches that essentially were sort of starting with something like a Latin hypercube design and augmenting it so that the result was still something like a Latin hypercube design. And what I find surprising is these methods just ignore the output. I mean, they don't use much, if any, information about what you've observed, particularly the space filling, and yet they beat methods that involved criteria that used more information. So this seems counterintuitive. Less information is better than more information. I have some thoughts about some of the reasons for that, but they're just conjectures. So anyways, I found that surprising. And so some of this was the motivation for our work. And to be more precise, what we decided to focus on, is it possible to implement some of these improvement criteria in a batch way? And the answer is yes, and you'll see as I start to tell you some of the approaches that we adopt, you probably think of a bunch of others too. So they're not real deep, but you'll see. So as I said, our goal is to find ways to implement one-at-a-time sequential methods based on an expected improvement criteria in B batches of m greater than 1 inputs. The one thing that doesn't work is just say, take the best m x's, because they're all the same point. You've got a continuous thing, and if x is the maximum of that, what's the next highest x? Well, for a continuous function, I don't know what that next number is. So if 1 is the maximum, what's the second highest value? So that doesn't work well. So you need to do something a little different, and as I said, if you think about it a little bit, you'd probably stumble on the same things that we've thought of. So here's one, and my student loves to give names for some reason, so I can't take credit for these. So here's one way. So the first point you select in a batch is the site with the best expected improvement. So you're applying the one-at-a-time criteria. In selecting subsequent points, all sites less than some user-specified distance from any site already selected are removed. So you're putting like a little ball or a little square around a point you've selected and say you can't take anything inside that. And Alex, I think, had something like that to try to avoid replication at points where the simulator just failed. So that's one thing. Okay, so that forces you away from a point you've already observed, spread things out a little bit. So that's one possibility. Here's another one. So this is a little strange. So you divide x, so you're going to do something like a Latin hypercube design. So you divide x into m to the d cells, a kind of a grid of identical dimensions. And then what you do is you find the point with the highest expected improvement. That's in one of these cells. Then you cross out all cells in the same row and column and so on. And then from the remaining cells, you find the point with the next that has the highest expected improvement. And then you cross those out. And when you're done, you're going to build a Latin hypercube. So here's a little example. So I've got this 3 by 3 grid here. I don't see the vertical things aren't coming out very well. And I take a point there. Maybe that has the highest expected improvement. So what's on my display isn't showing up. So unfortunately what I see on the screen isn't showing up here. So I cross this out and I cross this out. So the only cells left are here, 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 and here. So think of this as a 3 by 3 grid. So I take the point there. Now I can't take anything here, 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 or here. Here, 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 or here. So I have to take something in here. So I search in this little cell for the point with the highest expected improvement, and it's there. And so when I'm done, this point had maximum expected improvement. This had the next highest expected improvement from amongst all the cells that were still available, and then finally here. So you get a Latin hypercube, and you've tried to use expected improvement in some way. So that will be space filling, and it's still trying to use the expected improvement criteria. Another thing is to try to take advantage of something like a Sobel sequence. So that Sobel sequences have this property that if you start anywhere and keep going, it still fills everything out. So you just take you take a large series of points of a Sobel sequence. You find in that finite collection of points what point has the highest expected improvement. Then you take the next m minus 1 points after that in the Sobel sequence, remove those points to start the next batch, and go along. And now what's the point with the highest expected improvement in this long list of sequence of points? Take that point as the first point in your next batch, fill out the rest with the Sobel sequence. So you're getting a space-filling design that's still utilizing expected improvement. Since Sobel sequences don't work tremendously well, whether this will work well or not remains to be seen. But that's a possibility. You can impose a kind of distance penalty. So you say, I multiply my expected improvement by something that makes this smaller if these two are close together. So if these are the same point, maybe this should be 0, so there's no improvement, so there's no motivation to pick a point close to anything you've already taken. So some sort of distance function maybe could be used as a penalty. So penalizing yourself if you take points that are too close together is another possibility. Or you could do something a little more sophisticated where it's a general function of these two things that's strictly monotone increasing in each argument. So that's another thing you could do. So you're utilizing improvement, but avoiding some of the problems that come when you try to implement improvement in a batch manner. Here's another possibility. So you can see I'm just throwing out possibility after possibility. So you can only take, so what you do is you say, in my region, what's the subregion where the improvement's bigger than some number? So there's some minimal improvement that we have to obtain. That may be some disconnected, strange-looking set, and you somehow want to take a space-filling design in this set. Okay? And of course, the challenge is how to do that since this set isn't a nice interval, a nice region. But you could sort of just take random samples and only retain those points that fall in the region. So you could use something like uniform random sampling to do that. Or you could, again, try to employ this idea of a Sobel sequence and just take a long Sobel sequence and only keep those points that fall in this region and so on, so that you get something that's space-filling but still has some improvement. So that's a possibility. Another possibility is to do something like, well, and again, I think Alex may have referred to this or something like this in his talk. So what if the first point that I get that has the highest expected improvement, I evaluate my emulator at that point and pretend that's what the simulator would have given me. So I act as though that was really what I would have observed, add that to my data, so now I'm not going to resample that point anymore, refit my predictor, see what the improvement is, where I would take my next point, pretend that's what the simulator would really give me, add that to my data, do that till I get my m points, okay, and then then actually run the simulator at those m points and proceed. So I act as though what I get out of my predictor is actually what the simulator would have given me. So that'll move points around and avoid some of this. So who knows whether that'll work well or not. So, and I'm sure you can think of lots of other cases. So I said, we've come up with half a dozen possibilities. We could go on forever here and never make any progress. Let's just see how this works in a toy example. So we looked at the Brannon function. That was a function that Jones and so on used to try to demonstrate how powerful their improvement method was. So this is the Brannon function. It's I put it on the range -5 to 10, so this isn't quite consistent with my unit square measurement. But originally the Brannon function in this form, x1 ranges from -5 to 10, x2 from 0 to 15. There are 3 global minima that are tied, and these are the inputs at which you find those global minima. And so that's what it looks like, and you can sort of see that the minima are sort of down kind of in here somewhere. So we tried to implement these, and Aaron said, well, I'll start with an initial maximum Latin hypercube design consisting of 20 sites, and then start adding points in batches of 5 and just see what happens and compare it to what Jones and so on find when they do theirs at one at a time, just to see what happens. So to try to, I don't know how well this next graph will come out, but this is to try to demonstrate where the points, where you end up observing points. Here's what we get. So this is a kind of small thing. This is the one at a time method, and these are the 3 minima, and maybe you can move it forward so there's a slightly bigger picture of it. So these little green dots are your initial space filling design, and to be consistent with what Jones and so on did, we used a maximum Latin hypercube design. Then what happens is you essentially very quickly start zeroing in on where the minimum are, and you just keep resampling them over and over again, jumping from one to the other. So you have a big clump of red dots, and you just jump from them. And the beauty of the Jones algorithm is it finds all the minimum. Some of the other methods, so this is the, if I can remember which ones are which. This is the Latin hypercube thing, and while it's sampling around there, it's being forced to spread points all over the place. So it doesn't concentrate a lot of observations where the minima are, although it visits them, and it seems to particularly focus over here. So here's two of the other methods here that with the Sobel sequences and so on, where the distance penalty, again, they try to hit where the minimum are, but they also take lots of observations in other regions, so they have some space-filling properties. Here's another set of some of those methods. And in these cases, you can see that these 4 methods tend to cluster much more heavily around the minimum, much more like the one at a time method, and don't put a lot of observations out in the boundaries. Here's the solutions they arrive at, and my student is still getting his feet wet with programming. So what he did is he was looking, he set up a grid of points to sort of search for the optimum over. So that's why some of these numbers are 3.25 and consistently, because he wasn't always doing a global search, but just searching over a finite grid of points in the region. And whatever method, one at a time, this Euclidean distance-based method where you put a little circle around the points, the Latin hypercube, the Sobel sequence, and so on, you can see that for the most part, they seem to be identifying the optimum given these constraints about the grid and so on. Maybe there's a few, I mean, this doesn't look maybe quite as good as some of the other. I don't know about that. Where's one that, so right here, this may be a little off with the 2 and so on. But for the most part, they seem to find the minimum. Of course, you ran this for a long time. And they allow you to implement this in batches and to a greater or lesser extent have some space-filling properties. So this is just one example, and it's really all we've explored. So this is kind of a proof of concept sort of talk. How would you do this in batches? Here are some examples. In this simple Brandon example, they perform somewhat differently in terms of how much they do local searches at the minimum and how much they're space filling. What would be interesting is not only to try this on other examples with this improvement criteria, but to return to the example that motivated Moore, Lewepke, and Williams. And that example was to try to find designs that gave good global fit. So how do I add points in batches so that the emulator fits well globally? The challenge there, of course, is to try to think of what are improvement criteria that you would use for that purpose. But ultimately, that's the kind of thing we'd like to explore. So I'm going to stop there and see if there are questions.
Thanks, Bill. Sorry, we have some questions from the audience.
Yeah, your method where I think you used the emulator prediction, pretended that was the same.
Right.
If rather than taking the mean of the emulator, so you sample from its distribution, and that then sequentially led to very different choices for subsequent points, might that be a good way of learning where you need to put points to reduce your uncertainty about where you're going to find that?
Yes. So you're right. There's a lot of different ways I could do this, and what you're trying to do is use something from the observations you've had, use some criterion that's going to guide you, and yet not get hung up with but to be able to do this in batches, so that if you can run this in batches, that you can do that. And so yes, that would be certainly another way. And I have no idea what's really the right way to do this. These are sort of, as I said, this really needs to be tried out on quite a number of examples to see what kind of examples do different things work well in. So yes, that would certainly be another. Yes.
I think one thing that we have to be aware of, and many methods might fall foul of, probably the one you mentioned, is that this is an incredibly difficult subproblem, finding the maximum of the expected improvement in a 20D space. You can throw a massive genetic algorithm at it and maybe never get anything above machine precision. Your minimum number you can obtain. So I think some of your methods where you're saying, well, let's find the optimum there, or knock out some area, then find an optimum there, they will be computationally intractable. So what many people do is they use some method to find starting points for a multi-start gradient descent method, somewhere in between the sample points you've already got, because that's a good guess to begin with. And then what happens is you get loads of multiple optima out of the expected improvement function, or it's very likely. And I don't know how this is moving into a question. Did you consider just using all of the local optima of the expected?
Oh no, we haven't done anything sophisticated at all. So all the numerics you're talking about, are sort of lurking in the background. In fact, my student was running into enough problems where that's one of the reasons he kind of restricted this to a grid. So I said you're beginning to see some of the issues you're going to have to deal with, these computational issues and so on. I mean, I suppose in some sense that it reminds me of back in the old days when people were beginning to do computer searches for de-optimal designs and so on. And again, you all have all these numerical issues about how do you find the optimum and what are you going to do when the problem gets sufficiently big and so on. And we haven't solved I don't have any great insights into the computational issues, except that I realize that there are a variety of approaches that you can use. And in some sense, I'm really more interested in formulating criteria and trying to understand to what extent they're good or bad criteria for these purposes, and then being constrained by what I can do numerically to try to really explore these criteria. So I've kind of punted on your answer.
May I follow up
Yeah.
with Alex's remark? There are many local optima, that's what you said. Now it seems that natural if you do things in a batch, let's say a batch of 10, that you take the 10 best local optima.
If there are 10 best
I think there might not be 10.
Yeah, that's the problem.
You take the 10 best.
Well, there might be 3. There might be
But,
one.
but if suppose there's a single peak, what are the 10
That
best
probability is
points?
0.
That's the problem. They're the same point.
Fire away.
Yes.
In his thesis, Matt Schonlau proposed the multi-points expected improvement, which gives you the joint expected improvement of a set of points.
Right.
Did you consider that?
No, and in fact, no, I didn't. And what we decided to do was to look at the one at a time thing here. How do I want to say this? The real motivation was this problem that William and so worked on, which was sort of criteria for global fit. And the improvement criteria they were looking at didn't lend themselves to this sort of thing. So I was aware that Schonlau and so on had a batch sequential method for implementing that. But as far as I could tell, that there wasn't a way to take that method and transport it to the problem that Williams and so on were looking at. So rather than implement that, I decided to sort of look at other methods that would work in their problem. So the goal is really to return to the situation that they looked at. But I thought we'd try it on an easier problem first, because if it really did something goofy, then trying it out on more sophisticated problems was going to be an issue. Yes.
But just want to talk a little bit different. So Sobol sequences have the property of being net.
Yep.
And I just wonder if you try and relate your batch size to the right number so that the net property would be sustained. Have you tried that? Or because you use batch size 5, I think.
Yeah, that's right.
And well, that would be more restrictive, or it would be like a power of 2, like batch size 8 or 4.
Right. I mean, that's right. You have to worry about powers of 2 or powers of 3, depending on how you generate the Sobol sequence, what kind of prime number or Galois field you use to generate it. I think he was using MATLAB will generate these Sobol sequences, and the ones in MATLAB are all based on powers of 2 and so on.
But did not try the.
No. As I said, this is pretty early going, so as I said, it's kind of proof of concept. Yes.
So I have 2 comments actually. One, I don't think you have to refit when you add the new point because you've already got the parameters.
And then he did. I mean, he just kept using the same.
Oh, okay. So he said that he was refitting as part of the thing, and that would be There's also a theory there's a theorem in information theory that for stationary Gaussian process, that sequential addition of points for IMSE, at least as an asymptotic result, you will not do better than just straight Monte Carlo. So for IMSE, for a stationary process that is truly stationary, you should not do better by sequential addition of points.
Asymptotically.
Asymptotically, that's true. I mean, but most of the processes actually aren't stationary.
Right. Well, and I mean that's somewhat consistent with what Williams found, that they tried this batch
And that's why.
mean squared error, and it just didn't perform well.
Yeah. So this is not true for maxima and stuff like that, but just for the global fit, you shouldn't necessarily do better. So, all right. I think we're out of time. So why don't we thank Bill one more time?